All right, hey everybody. So today we're hitting two more models, which are also under the umbrella of ensemble methods. However, yesterday we covered bagging. Today we're going to two 2/3 boosting methods. Why it's three, maybe two or three. We'll see why in a little bit. So today, what we're going to differentiate between bagging and boosting. The two ensemble methods, the two main subsets of named ensemble methods, as we talked about yesterday. Any model that uses a combination of models is an ensemble method. So we'll talk about the differences between bagging and boosting, and we're going to talk through two specific methods, eta boost and gradient boosting, how they differ and how they each make predictions. Now, the third one, which there's like one last slide at the end, it's called XG boost. If you've read or looked at Kaggle competitions, you might have seen XG boost. It is usually the top performing model in most scenarios. And XG boost is it comes from gradient boosting, but is in a separate library, is a completely different model. I'll talk about those differences at the very end. So technically we're hitting two kinds of boosting models, but we'll hit three different models that you could implement. So yes. All right, so boosting basically refers to any ensemble method that combines several weak learners and their mistakes into a strong learner. So yesterday when we talked about bagging, we don't really take into account that each decision tree is making, a bunch of errors. We're just hoping that overall, most of the decision trees predictions for each data point will be the right one, or it will aggregate to become the right one. But in boosting, you're actually making use of the misclassifications within each weak learner. And by weak learner, we mean each decision tree. So the general idea of most boosting methods is to train predictors sequentially, each trying to correct its predecessor. So whereas with bagging, we're kind of training everything in parallel, like the training of each decision tree doesn't affect the training of another decision tree. Boosting, you have to do it sequentially, and we'll see why that is when we get into the details of these two boosting models. So the most popular boosting methods are eta boost, which is short for adaptive boosting, and then gradient boosting. So quickly, bagging versus boosting. If we take a look at a single iteration, this is a single decision tree. This is what that looks like. If we're talking about bagging, which is what we did yesterday, of course, we bootstrap each data set over here, and we're pretty much building every tree. We could potentially build each tree in parallel. We talked when we talk about big data and PySpark, we can talk about how trees can be trained at the same time. The difference between bagging and boosting, you can sort of see through the arrows over here. Bagging, it kind of just spreads out. You can train all your trees at once, whereas boosting, you feed in some result from one tree to train your next tree. So over time and over each iteration, your trees should get better and better. All right, so boosting is a statistical framework where the objective is to minimize the overall loss of your ensemble model by adding weak learners using a gradient descent-like procedure. We'll talk about specifically those procedures and how they're different in the two kinds of boosting in a little bit. And it basically allows different loss functions to be used, expanding techniques beyond binary classification. And these also support regression, multi-class classification, and more. So yesterday we talked about how both the bag trees classifier as well as random forest actually do work in a regression. There are the regression models on scikit-learn as well. And same for these ones that we're going to talk about today. Both of the actually all three of the boosting methods we're going to talk about today have regression counterparts that you can find on scikit-learn or through XGBoost. And I'll show you XGBoost later too. Also similar to bag trees, how yesterday we talked about how we could substitute instead of a decision tree, you could technically bag a k-nearest neighbors or a naive Bayes, anything like that. You can do the same thing for boosting, and I'll show you all the documentation in a little bit. All right, so this is the intuition behind eta boost. So first, we're going to start with this data set. So this is our original data set, and let's just say we trained a depth of one decision tree. Depth of one means we're just splitting our feature space one time. So once that is done, we take a look and we see that this is the result over here. So with this result, what happens in AdaBoost is it looks at what was misclassified. And so over here, what we see is we have 2 minuses and 1 plus that are on the wrong side of this decision boundary. So what happens when we go to the next classifier is we're going to emphasize these misclassified points more. So as you can see here, it's not super clear, but the 2 minuses and the 1 plus over here are a little bit bigger. So we're going to emphasize our prior misclassified data points for the next classifier. So with this plus and these 2 minuses emphasized, we train another decision tree with max depth of 1. And we end up with a different boundary. And the different boundary here, you can see that instead of those being misclassified, we have these 3 minuses being misclassified. And that's just going to keep happening over and over again. And then we're going to combine the classifier, and we'll go into more detail about how this is done in the coming slides. But basically the idea here is what data points did your classifier fail to correctly classify? And we'll emphasize those errors and retrain the model. Any questions on this intuition? So you can see here, these 3 minuses were wrong. It's not very clear to see, but these 3 minuses are technically being emphasized here to train this classifier. And this can be done over and over again until you come up with some combined classifier. All right. Okay, so AdaBoost is basically an ensemble method that is used to solve classification problems. First, you initialize the weight of each of the observations to be equal. So at the very, very first classifier, the weight of each observation will be equal, 1 over n. So you first fit this base classifier. Like we talked about in the last slide, we first have this base classifier, we're fitting it, and then we're gonna make predictions on the training set. And then what we're gonna do is increase the relative weight of the instances that were misclassified. Basically the same thing as emphasizing these prior misclassified data points. And then we're gonna train another classifier using the updated weights. And then at the very end, when we have, let's say, 100 decision trees that are trained on different weightings of the data set, we're going to aggregate all the classifiers into one, weighting each classifier by their accuracy. So this is a little bit more detailed. Questions at this point? Okay, I think conceptually, you're just telling the model to capitalize on your prior errors and retrain your model, making sure that you try and catch those errors as good as possible. Okay, so this next slide, there's a lot of math in it, but I'm going to talk through some parts of it because I do think it does help with intuition for some people. So first, we're initializing observation weights over here. So weights being 1 over n, meaning every data point that you have is going to be considered equally, which at the very start makes sense. So for our m equal to 1 to m, this means that we're going to fit up to m classifiers. Let's say big M is going to be 100. So we're going to fit 100 decision trees sequentially. So for the first one, we're going to fit a decision tree using these weights. So this is just at the first iteration, all the weights are equal. This is our decision tree. Then we're going to compute our error. Now, this error is literally just our accuracy rate. Because if we look at this, it's just how many were misclassified. What this means is actual data is not the same as predicted data. The math and how this is notated, not super important for now, but that's what this means. And also weighted. So let's say our data points right now are all weighted the same, so this actually doesn't matter. Next, we're going to compute an alpha, which is basically the overall accuracy rate. And then we're going to update our weights. And after we update our weights, these steps C and D are basically reweighting our observations so that it'll look at our misclassified instances with more. It'll just look at our misclassified instances more for the next classifier. And this step just repeats until you're done fitting all your classifiers. Then at the very end, we sum all of our classifiers and predictions together using this alpha. So this alpha is basically an overall error rate. And then so we're going to take a weighted average of all of our classifiers to get our final prediction. The main concept to grasp with AdaBoost is the fact that you are just capitalizing on your prior mistakes. Any questions here? I realize I've drawn a lot of boxes. Any questions at this point? All
Oh,
right.
is it, oh,
Yeah.
is it looking at, like, when you say it's a capitalizing from a loss, it's the loss function, not necessarily like the coefficients, right? That's what you mean, right?
So it's capitalizing on misclassifications. And so
Yeah.
at this point, the loss function or the cost function here is really just the accuracy rate in this case specifically, using
Got it.
this in this specific equation. I will tell you that also in AdaBoost, you can have different cost functions too, but typically you just want to see misclassifications.
Perfect. Thank you.
You're welcome. Anything else? Okay, so let me clear this. Okay, next, one additional detail is that the first classifier is actually being trained on a random subset of the overall training set. So let's just say you have 1,000 data points in your training set. At the very start, you're gonna just train it on 800 out of 1,000 of your training data points. Then things that are misclassified are assigned a higher weight. And what this weight is actually the probability of it being selected for the next iteration of training. So when I say the weights of the data points and looking at a specific data point with more, or considering a specific data point more in your model, this is what I mean by that. Is you're taking a fairly large random subset of your training set with each iteration of your model, for each iteration of weak learner. And then, yeah, basically your misclassified data points have a higher chance of appearing in the next training set. Cool. So this is the weighting of the classifiers. Let's say you train 100 sequential decision trees. These equations not super important, but just to understand that more accurate classifiers are assigned higher weights to have more impact on the final outcome, right? If let's say your very first decision tree did not perform well at all, you don't want their prediction, or you don't want its prediction to have as much weight as maybe one of your last few decision trees that has a very high accuracy rate. So that's how it aggregates all of those decision trees that you've built. Cool. So in regression versus classification, the only difference is the cost function that is being used. So for cost function for classification, we talked about that earlier, is basically what was correctly misclassified. Sorry, what was correctly classified and what wasn't. But for regression, you're going to use a loss function. And very likely the loss function is actually mean squared error. So how accurate were your predictions? Cool. All right, so now by thinking of boosting, and actually this is quite similar, these things to think about are quite similar for all boosting methods. First, think about the quality of your data. Because the way that this boosting ensemble method works is it attempts to correct misclassifications in the training data, you have to be careful that the training data is of high quality. What exactly does that mean? Think about outliers. So if you have a few outliers that are not representative of your overall training set, it'll kind of force your ensemble down the rabbit hole of working hard to correct for cases that are unrealistic. So these could be removed from the training data set. Instead of removing them, I'll show you all later a couple graphs where you might not need to do that. But if you think about it, if you allow your model to build like thousands and thousands of sequential trees, it'll eventually overfit to your outliers. Same for noise. I mean, the difference between noise and outliers can be very similar, and I feel like these are not mutually exclusive, but noise can also be problematic, especially noise in the output variable. So if you have, if you're trying to do a classification problem, and let's say you have 10 classes, 2 of your classes make up 90% of your data, and then maybe your other 8 classes are like a few points here and there, that can actually lead to really weird overfitting in boosting models. So if possible, attempt to isolate and clean these from your training data set. This is really only in your target variable. All right. So in summary, for AdaBoost, sequentially trains classifier, and it improves the classifier by looking at misclassified instances, and then weights misclassified instances more, so they're more likely to be included in the next training data subset, weighted based on their accuracy when they're aggregated, and then things to consider: doesn't perform well on noisy data or outliers, and it can also use any kind of classification model, not just a decision tree. While I pull up the documentation, any questions? Boost. I can learn. I recently cleared all of my cookies, so all the suggested results don't come up. Oh, dark theme, nice. All right. Okay, so this is the AdaBoost documentation. And the main thing I want you all to see here is base estimator. So base estimator, you can pretty much give it whatever instantiated model object you want. So here, what we're doing is the base, by default, the base estimator is a decision tree classifier initialized with max depth of 1. So this is the default, and it's a max depth of 1 just because you want it to slowly learn misclassified instances. If you start with a max depth of 5, what happens is that you have fewer misclassifications, or you might have fewer misclassifications to go off of. It starts to overfit very, very early on. The idea of boosting is even more important, I would say, versus bagging, to use a very weak learner and have it slowly learn over time. Other parameters to consider here, you have n estimators, the maximum number of estimators at which boosting is terminated. Basically, how many sequential trees are you going to build? Learning rate you shouldn't need to mess with. I would say when you are tuning parameters, you can actually tune parameters of your base estimators if you want as well. But usually the main parameters that you tune, if not base estimator, is actually the number of estimators. And when we get to gradient boosting, I'll show you all a couple graphs that we'll talk about how you can tune that hyperparameter. All right, questions? All right, so if there are no questions on AdaBoost, next is gradient boosting. And gradient boosting basically will very similarly evaluates a collection of trees sequentially, just like AdaBoost, and Ensemble is a collection of trees that model the underlying behavior of the data. However, the difference is, instead of looking at specifically misclassified data, Gradient Boost evaluates the residuals of the previous tree and tries to make predictions on the residual, which is kind of interesting. And because there's this whole idea of residual, we're going to use more regression to talk about this. Okay, the math for this is a little bit complicated. We may or may not come back to this. So let's just say we start with data that looks like this, and we want to fit a regression model. What we're trying to predict is y over here, doesn't matter what y is, and let's just say we just have x to start. And what we're going to do is you're going to try and fit a bunch of regression trees to try and predict this data. So this is what gradient boosting tends to look like. So what'll happen first, and basically what we're going to do is for every tree, we're just going to do a max depth of 1. So with a max depth of 1, let's just say the first split here is saying that, okay, if x is smaller than 30, the prediction will be 11. If x is greater than 30, the prediction will be 20, like 22, for example. And that is this example of the very first iteration. So, okay, we fit our tree of max depth 1 to this data. That's what our prediction line looks like. The red line, this is our prediction at our first iteration. Now, because gradient boosting looks at our residuals, let's plot these residuals. So this actually starts at 0. I forgot the labeling over there, but let's just say this graph starts at 0 over here. That's kind of 0. And because the line fits perfectly over here, there's very little error over here, positive error here, negative error here, positive, negative errors here, based on how far away these clumps are from the prediction line. So we're going to take these residuals, and what we're going to do is we're going to overlay another regression tree on these residuals. So what will happen is we'll build another decision tree with max depth 1 on these residuals. And I don't know exactly what this is going to look like, but what happens here is our line gains a little, it learns a little bit more. So at iteration 2, and this is still 0, by the way, or roughly 0. At iteration 2, we learn a little bit more based on these residuals. Whatever our second decision tree has learned is basically learned to fit, based on this, it's learned to fit this part of our data. So that's how that has much lower error at this point. And so by refitting decision trees over the residuals, over time, the residuals will all start to go to 0 because you're trying to fit a regression line to best fit these outcomes over and over again. And so as these start to converge to zero, as you can see here at iteration 3, it's starting to get a little bit closer together. By iteration 18, 19, and 20, the residuals are all around 0. And of course, I keep forgetting to add the labels to these, but the 0 moves till down here because the errors for your regression will all converge to 0 over time. And of course, if you keep doing this over and over again, by eventually all your residuals will pretty much hit 0. This is a little harder to conceptualize just visually, just regressing on the residuals, but any questions on this that can help clarify?
Just a quick question. How many is the point just to get the residuals down to 0? Doesn't matter how many times, how many iterations? That's
Yeah, great question. That's actually what I'm going to talk about next. So you can imagine that if we get all of our residuals to 0, that's great for our training data, but it might not do so well on our testing data, dependent on how our data is distributed across our training and testing set. So typically you don't want to get your residuals all the way to 0. What you want to do is you want to actually keep track of your train and test metrics and make sure they don't start to diverge. I forget if there's a graph that will show that in a neat way, but I'm going to talk about this, like when do you stop doing these iterations? Yeah, anything else before we move to that? You're welcome, Mo. All right. Drawing dots, hold on. Okay, so typically the more trees you do, the lower your error. At some point, your validation error or your test set error is going to start to diverge as your model starts to overfit. So as I was kind of alluding to before, the more iterations you do for any boosting model, the more likely your model will start to overfit. Because one, in AdaBoost, it's learning from all these misclassifications, and at some point you're not going to have any misclassifications at all. Your train set will have perfect classification, same for gradient boosting as well. But it has for your test set, it's not guaranteed that that will happen as well. So let's just say with this example, we're taking a look at our testing error. And our testing error, let's say, starts at over 1%. And at some point, as your model learns, it gets better and better. But at some point, as it starts to overfit, you will see that your validation error will slowly start to go up. And that's a very normal thing to see when overfitting happens, right? When you see that your train error is doing much, much better than your test error will start to get worse over time. So what you might see, and it's not on this graph, but imagine your training error. Training error is usually lower than your test error. So what's normal to see is your training error looks something like this. And then at this minimum point, it's normal for train error to keep going down as it starts to overfit while your test error starts to go up. So, okay, at this minimum, which is what I determined to be my best model, and actually if you do grid search, it will show you the same thing. At its minimum, the number of trees is 55. So 55 iterations give for whatever this problem is, happens to be the best. And this is what that model looks like when you plot the regression output. The next one will be a little bit more clear to talk about overfitting and underfitting. I hate that it's super unclear. But anyways, you can see that here we have 3 estimators. With 3 estimators, this is what our line looks like for the same data that we had before. So with 3 estimators, this is what our line looks like. It's trying to best fit our line with only 3 max depth of 1 decision trees. And this is an example of overfitting. This is 200 estimators fit to the data. You can sort of see that there's some overall, there's a lot of jagged lines that might be a sign of overfitting versus something like this that's overall a little smoother. Of course, you have a little bit of that jaggedness, but it's just trying to fit it to the data. But you can see that this is much more overfit because the more iterations of trees that you have, the more your regression line has the opportunity to account for all of the outliers, the patterns in your data. So when you're trying to tune a boosting model, that's something that you should look out for. Basically, keep track of your training and testing metrics, especially when you're tuning your N estimators parameter. to make sure that it's not starting to overfit. Cool. Questions about that? All right, so I'm going to pull up the gradient boosting classifier. Gradient boosting. You can see that there's a classifier and a regressor as well. So let's take a look at the classifier. You can see that here, n estimators, the default is 100. So by default, it's going to run 100 different iterations of trees. I think by default as well, it is running, let me see, where is it? Somewhere it says that the regular is decision trees. I cannot find where that is. Decision trees. There we go. So the estimators, it is shouldn't be a regressor, but never mind. Somewhere it says that the decision tree classifier is the base estimator that's being run. I can't find right now. Never mind. Not important for right now, but just know that you're building a bunch of decision trees over each other to do that. And the main thing that you want to tune is n estimators. But within this, you can see that we know that is trees because all of the hyperparameters are same as our tree parameters, right? Our min sample split, min sample leaf, max depth. Oh, I guess it starts as a default of 3, but same idea, just a bunch of trees over and over again, training on the errors on the residuals of its prior model, of its prior weak learner. All right, questions about this? Okay. All right, so same regression versus classification. For regression, you're minimizing the cost function by finding residuals of prior tree. Basically, what you're doing is you're looking at the error from the last tree, regress on the error. It's like if you were to take your residuals from a linear regression, you're building a regression on your residuals of your regression. For classification, it's slightly different in terms of how it calculates residuals, because for classification, there isn't really residuals. What it is it's maximizing log likelihood. So very similar to how you go from regression, linear regression to logistic regression. It's a very similar switch. Instead of looking at overall, mean squared error or mean absolute error between your predicted and actual, you're looking at log probabilities or maximum likelihood estimation, which the math is really not important for this part. So what you're doing is you're just going to keep creating new trees based on those gradients on how it thinks it should improve. Questions about this part? All right, so that is gradient boosting. Gradient boosting, it's very similar to what it was before, capitalizing on the mistakes of its prior learner to get better and better. Now, the next model I'm going to talk about is XGBoost. And let me just pull this up over here. XGBoost, it comes from a different library, but it's basically a type of gradient boosting as well. And I have a slide on it here too. Right, so XGBoost and GBM is also from XGBoost. Both follow the principle of gradient boosting. However, there's a slight difference in the modeling process. What XGBoost is, it has regularization built in. So as we saw, gradient boosting by itself has a tendency to overfit just because it's trying to capitalize on its prior errors, which makes sense. That's how a model tries to learn, but it starts to overlearn the training data. So XGBoost kind of controls for that on its own, which does give it overall better performance because n estimators, the more estimators you do, it doesn't cause overfitting as much as just regular gradient boosting. So XGBoost actually refers to the engineering goal that is used to push the limit of computation resources for boosted tree algorithms. So what's really cool about XGBoost is something in its backend just makes it a lot more efficient to train. So if you were to implement gradient boosting in XGBoost, even though they follow very, very similar modeling approaches conceptually, how it is coded out and built out in the backend, XGBoost performs a lot faster. What it is I wonder if it's over here. It basically uses, it tries to do parallel computing on sequential trees, which is something we'll talk a little bit more about when we get to big data next phase. So some pros and cons really quickly. XGBoost is not powered scikit-learn. However, the model works exactly the same. There's still the .fit, .predict. What's even better actually about XGBoost is that it has its own feature importance function that automatically creates the graph. So you don't have to like look for the plot to plot out the feature importances graph. So XGBoost over here, let me see if I can find it here. Oh, by the way, all the parameters are the same. In terms of parameters, you have max depth over here, child weight, bunch of different tree methods here. Let me see if they have plot feature importances. Actually, I should look for importance. Okay, I guess it's not here, but through here, if we look up XGBoost feature importance, let's see if there is an example here. Cool. From here, yeah, you can see that XGBoost has a plot importance function within it. So it automatically gives you the feature importance. Of course, for your data set, you can configure it to look a little bit nicer than this. But yeah, so it's harder, better, faster, stronger. You can also use any cost function. At this stage, we don't need to tinker with the cost functions, but if you wanted in the future, if you get more familiar with cost functions, you can actually implement your own custom cost functions, which is cool. In terms of the cost function though, if you are familiar with cost function, honestly, I am barely scratching the surface of cost functions myself, but you have to make sure that your cost functions are twice differentiable. So something like root mean squared error is twice differentiable because you can differentiate it or take the derivative of it twice. Also, yeah, it has built-in regularization, L2 by default based on node weights. And we'll get more into node weights and what that means when we actually get to neural networks later on. But yeah, those are the 2.5 boosting methods, eta boost and gradient boosting. XGBoost, yeah, it's just been demonstrated to perform very, very well. All of these Kaggle competitions, a lot of them are won with XGBoost. So yeah, cool. And a couple resources linked over here. If you want to take a look at these are here for you. But yeah, any questions on boosting at this moment? All three of these models that we talked about, your function that I think all of you here have shown me some form of your function will work. Your function will work if you instantiate these models with them. Cool. Mm-hmm.
Yeah, I had a couple of questions. First, for the validation model, for the validation error,
Yes.
is it fair to say, or is it correct to say that once it plateaus, that's it? Like once it flat, then, stop making any more trees?
Yeah, that's right. Like something that you could do for a boosting model if you can. I mean, this will be kind of hard to incorporate with your function as well. But if you wanted to really explore or go dive deep into a boosting model, you could set the number of estimators to be very, very high, and then take a look at your validation error with different number of estimators. And so, yeah, typically what you see is it gets better to a point and either starts to plateau out or gets worse. So either once it starts to flatten out, that's a good place to stop.
And I tried to, I mean, we could discuss this for a one-on-one, but I tried to install the XG booster and it was not, I don't, for some reason it wasn't
Ooh, okay.
through, so
weird. Okay, yeah, that we can definitely talk about at our one-on-one, or if no one has any questions, we still have time, so I'm happy to talk about it right after this as well.
all right, no problem. Thank you.
You're welcome. Any other questions for today? All right, sounds good. Well, Slack me if y'all need anything. I'm gonna stop the recording here.